In this video, let's take a look at what Bayes' theorem is and see what kind of problems it can handle. First of all, let's take a look at this situation. Suppose the probability that James will study for a test is 0.3. If he studies for the test, then the probability that he will pass is 0.6. If he does not study, the probability of passing in the test will then be 0.2, which is smaller. Now the question is that if we know that he passes in the test, what is the probability that he has studied for the test? This situation can be illustrated by this tree diagram. In the first place, there are two cases, studying or not studying. For these two cases, both can result in an outcome of passing or not passing. And these are the probabilities given by the question. There is a 0.3 chance for James to study. If he studies, there is a 0.6 chance to pass in the test. If he does not study, there is still a 0.2 chance to pass in the test. From the complement law of probability, we can obtain the probabilities of the other branches. So we know that 1 minus 0.3 is 0.7, 1 minus 0.6 is 0.4, and 1 minus 0.2 is 0.8. Using the notation of conditional probabilities, these probabilities can be denoted like this. This 0.6 is the probability of passing in the test, given that James has studied. And this 0.2 is the probability of passing in the test, given that James has not studied. Therefore, for the probability that James studies for the test and also passes in the test, according to the multiplication law of probability, it is equal to P study times P pass given that study. So it is just the product of these two probabilities. As such, we can calculate the probabilities of all these four cases. And these four probabilities should add up to 1. Now to find the required probability, it is equal to the conditional probability that he studies for the test given that he passes in the test. According to the formula of conditional probability, PA given that B can be written as PA and B over PB like this. For the numerator, which is the probability of studying and passing in the test, it is simply equal to this value, 0.3 times 0.6. For the denominator, which is the probability of passing in the test, this event should be the result of one of these two branches. So according to the addition law of probability, we should add up the probabilities of these two cases like this. As a result, the required probability is equal to 0.5625. From this example, we can see that in order to find P study given that pass, by using the formula of conditional probability and expanding this numerator with the multiplication law of probability, we can obtain a relation like this. And this relation shows us how P study given that pass and P pass given that study are related. From this formula, we can see that the ratio of these two conditional probabilities, P study given that pass to P pass given that study, is equal to the ratio of their unconditional probabilities, P study to P pass. And this result is known as Bayes' theorem. From this example, we can also observe that this denominator can be expanded in this way. In order to calculate the probability of passing in the test, we have expanded this event so that it becomes studying and passing or not studying and passing. If we denote the event of passing as B and the event of studying as A, then we can obtain that PB is equal to PA intersection B plus PA prime intersection B. And this result can be illustrated by a Venn diagram like this. Essentially, it is the result from the addition law of probability. But this time we are not expanding PA union B into simpler probabilities PA and PB. Instead, this time we expand PB into more complicated probabilities PA intersection B and PA prime intersection B. In mathematics, this result is specifically referred as the law of total probability. Besides expanding PB by considering two events A and A', in general, PB can be expanded by considering more than two events. If these n events A1, A2 to An are exhaustive and mutually exclusive. Exhaustive means the union of these events will cover the entire sample space. This situation can be illustrated by a Venn diagram like this. The events A1, A2 to An are exhaustive, so their union is equal to the sample space S. Also, these events are mutually exclusive, so their pairwise intersections are all empty sets. Using the multiplication law of probability, this expression can be further expanded in this way, and that is the law of total probability. Now we can see that this formula of Bayes' theorem can be further expressed in this way, because the denominator can be expanded by the law of total probability like this. In this formula, we can relate the conditional probability of studying to the unconditional probability of studying. In the context of Bayes' theorem, this unconditional probability is known as the prior probability of studying, and this conditional probability is known as the posterior probability of studying. The prior probability of studying means the probability of studying that we can know before we have any extra information about the situation. And the posterior probability of studying means the probability of studying that we can know after we have obtained extra information about the situation. In this case, the extra information is that we know James passes in the test. Usually, prior probabilities can be directly obtained from experiments and observations. But for posterior probabilities, we may not be able to obtain them directly. So, Bayes' theorem is important in probability theory not only because it tells us how P study given that pass and P pass given that study are related, but because it also tells us how the posterior probability can be obtained from prior probabilities. In general, for any exhaustive and mutually exclusive events A1, A2 to An, the posterior probability PAI given that B can be expressed in this way by Bayes' theorem. This numerator is just this shaded area in this Venn diagram, and it is also one of the terms of this expression in the denominator. Now let's take a look at this further example and see how we can apply Bayes' theorem. In a secondary school, we know that the numbers of S3, S4, and S5 students are in the ratio of 3 to 4 to 5. If these percentages of students are prefects, and a prefect is randomly selected, what is the probability that the selected prefect is an S5 student? In this context, we know that the unconditional probability that a chosen student is an S5 student should be 5 over 3 plus 4 plus 5, which means 5 over 12. Now we further know that this student is a prefect. So we are indeed interested in this conditional probability, PS5 given that prefect. According to the formula of conditional probability, we know that it is equal to PS5 and prefect over P prefect. And then for the probability that a student is a prefect, there can be three cases. The student can be an S3 prefect, an S4 prefect, or an S5 prefect. So P prefect can be expanded like this by the addition law of probability. Or more specifically, that's the law of total probability. Now each of these probabilities can be calculated by the multiplication law of probability like this. Hence the required probability is equal to 25 over 51. As we can see, even though we do not apply the formula of Bayes' theorem directly, by just considering the multiplication law and the addition law of probability, we can also obtain the value of this posterior probability. Therefore, although Bayes' theorem is important conceptually, it may not play a key role algebraically. As long as we know how to apply the multiplication law and the addition law of probability, Usually, it is already enough for us to handle this kind of probability problems. This is how we can understand Bayes' theorem in probability theory.